Today in calculus, we will be learning optimization problems. To start off, let's look at the definition of optimization. Optimization. To optimize the situation is to realize the best possible outcome subject to a set of restrictions. Because of these restrictions, the domain of the function is usually restricted. As you have seen earlier, in such situations, the maximum or minimum can be identified through the use of calculus, but might also occur at the ends of the restricted domain. So we will take a closer look into three types of optimization problems today. So look at how to solve optimal area, optimal volume, and to minimize distance. So let's look at some key ideas. Let's get this into focus. Alright. Number one. In optimization problems, you must determine the maximum or minimum value of a quantity. So that's really, really important. Second, an optimization problem can be solved using a mathematical model that is developed using information given in the problem. The numerical solution represents the extreme value of the model. So, last thing is key things to know. So, the algorithm for solving optimization problems. So, number one, understand the problem and identify quantities that can vary. Determine a function in one variable that represents a quantity to be optimized. 2. Whenever possible, draw a diagram. This is very important. Labeling the given and required quantities. 3. Determine the domain of the function to be optimized using the information given in the problem. 4. Use the algorithm for extreme values, I short formed it for A for x values, to find the absolute minimum or maximum value in the domain. 5. Use your result found in step 4 to answer the original problem. Obviously, I will be writing in pencil for my problems. This is just so you guys can see, and I'll catch you guys in a second. Examples. Let's talk about important definition. So, the first one I want to look at is domain. So, the domain of definition, or simply the domain of a function, is a set of input or argument values for which the function is defined. That is, the function provides an output or value for each member of the domain. Okay, max and min. The maximum and minimum of a function, known collectively as extrema, are the largest and smallest value that the function takes at a point, either within a given neighborhood or on the function domain in its entirety. I'm going to leave out optimization because I gave you guys the definition at the beginning of this lesson, so let's see if you guys remember that, and you can write that down for yourselves. And extreme values is another really important word. So the extreme value theorem states that if a real valued function f is continuous in the closed and bound interval square brackets a comma b, then f must attain a maximum and minimum each at least once. So there you have it. So now let's get started with our first optimization problem, which is solving a problem involving optimal area. So the question reads, a farmer has 800 meters of fencing and wishes to enclose a rectangular field. One side of the field is against a country road that is already fenced. So the farmer needs to fence only the remaining 3 sides of the field. He wants to enclose the maximum possible area and to use all the fencing. How does the farmer determine the dimensions to achieve this goal? So what we're trying to find is area. So let's set some let statements. So let's let the width be represented by x meters. Let's let the length be represented by 800 minus 2x meters. The farmer can achieve this goal by determining a function that describes the area, subject to the condition that the amount of fencing used is to be exactly 800 meters, and by finding the maximum of the function. To do so, the farmer also proceeds as follows. So that's what we just did. We found our let statements, and now we can go on to find the area. So area is length times width. So x times 800 minus 2x, we get 800 minus 2x squared. So next we will set a domain for ourselves. I found that it's 0 is less than x less than 400. Since the amount of fencing is 800 meters, to find the minimum and maximum values, we must determine a prime x, which is the first derivative. So let's set a prime x is 800 minus 4x, and then we have to set that to 0 to find the true max or minimum value. So when we isolate x, we get x is 200. To finish off this question, the minimum and maximum values can occur at x equals 200 or at the ends of the domain, x equals 0 and x equals 400. Evaluate investigating the area of function at each of these givens. So, A at 0 is 0, A at 200 gives you 80,000, and A at 400 is 0. So it's obvious that 80,000 is the maximum area. Sometimes the ends of the domain produce results that are either not possible or unrealistic. In this case, x equals 200 produces the maximum. The ends of the domain do not result in possible dimensions of a rectangle. So our final statement, the maximum area that the farmer can enclose is 80,000 meters square within a field of 200 meters by 400 meters. Type of problem is solving a problem involving optimal volume. So the question reads, a piece of sheet metal 60 centimeters by 30 centimeters is used to make a rectangular box with an open top. Determine the dimensions that will give the box with the largest volume. So here we have our picture of our box with the dotted lines represent the folds. So it's there's two sides, so we need to have X's on both sides of that square, those corner squares. So, by our diagram, we see that we can make H equals X, H is the height, L length represents 60 minus 2x, and width is 30 minus 2x. All dimensions are positive, therefore our domain is 0 is less than x, less than 15. To visualize this for volume more, we can make a rectangular prism, and we see all the dimensions there. Volume of the box is the products of its dimensions. So, volume is height times length times width, x times 60 minus 2x, times 30 minus 2x, 4x cubed minus 180x squared, plus 1,800x. From the diagram, also note, from the diagram, making the box requires the four corner squares to be cut out and discarded. Folding up the sides creates the box. Let each side of the squares be x centimeters, so also keep that in mind. So for extreme values, remember that term we spoke about, we set the derivative of the volume to 0. So 0 equals, all I did here was isolate for 12, because the derivative is 12x squared minus 360x plus 1800, but all I did was sub out the 12. So 0 equals x squared minus 30x plus 150. So obviously we can't factor that, so we have to use the quadratic formula, and you should get x equals 30 plus or minus root 300 over 2. That can be simplified to 15 plus or minus 5 root 3, which x equals approximately 23.7 or approximately 6.3. So since 0 is less than x, less than 15 is our domain, x equals 15 minus 5 root 3, which is approximately 6.3, is the only place within the interval where the derivative is 0. So next we want to do is find the largest volume, and I will be back, and we will sub our x that we found, 6.3, into the original equation. So by doing so, you will get 5,196 as our, cube meters, and that is your maximum volume. So maximum volume is obtained by cutting out corner squares of the side length of 6.3 centimeters. The length of the box is 47.4 centimeters. You will find that by subbing 6.3 into our equation for our length, and the width of the box is about 17.4 centimeters, and height is about 6.3. So that is all for that problem. I'm just going to read out loud because it's really long. So, Ian and Ada are both training for a marathon. Ian's house is located 20 kilometers north, as you see here in the diagram, north of Ada's house. At 9 a.m. on Saturday, Ian leaves his house and jogs south at 8 kilometers per hour. At the same time, Ada leaves her house and jogs east 6 kilometers per hour. When are Ian and Ada closest together, given that they both run for 2.5 hours? So do you guys follow? I hope you guys follow that. Just rewind the video back because it will be too confusing to write out, and I'm just going to get started. So first thing, we want to set our variables. So if Ian starts at point I and reaches point J after time t hours, then ij is 8t kilometers, and ja is 20 minus 8t kilometers. Now, if Ada starts at point A and she reaches point B after t hours, and AB is 6t kilometers, now the distance they are apart is s equals jb. And s can be expressed as a function of t by the square root of ja squared plus ab squared. And you just sub all the variables in, and you should get square root 100t squared minus 320t plus 400, and just change that square root to the exponent 1 over 2 because we will be doing the derivative. So, next thing, we want to set the domain. Domain is 0 is less than or equal to t, which is less than or equal to 2.5. Next, do the derivative, and you should get 100t minus 160 over square root 100t squared minus 320t plus 400. Remember, negative exponent, it's equivalent to 1 over whatever the equation is. So it would be 1 over the square root of this term. Next, to obtain maximum or minimum value, let s at t, prime at t, equals 0. So just sub this to 0. Obviously, the denominator negligible, it gets canceled out because 0 times that is 0. And then isolate for t, you should get t equals 1.6. So using the algorithm for extreme values, sub in all your values. So in the original equation, s at 0, you will get root 400, which is 20. S at 1.6 is 12. S at 2.5 is root 225, which is 15. So therefore, the minimum value of S at t is 12 kilometers, like they asked for the minimum in the question, which occurs at 10:36 a.m. And good job today. Homework, don't forget, is number 1 to 10 on the handout. Feel free to email me if you have any problems or further questions. Have a good night. Thanks for watching.